Dear students, welcome to the EPG Pathshala. I am Dr. Gurmeet Singh, working as a professor in University of Delhi's Chemistry Department. Today, we are going to discuss about the module High Resolution Electron Energy Loss Spectroscopy, which I have already said is abbreviated as HREELS analysis. Now, in this case, we have given you the introduction and we have talked about the instrumentation. Now, in this module, we shall talk about the way we carry out analysis with the help of this. This comes under the paper Surface Analytical Techniques Part 1. When you complete this module, you will be able to understand some basic facts. First, what is sample preparation? Number two would be data interpretation, then spectrum analysis, and the next would be HREELS for the study of adsorbate and surface chemistry. Sample preparation, when we talk about, would be one of the very important factors. One of the major challenges in the application of HREELS in transition in solid state physics and material science is the preparation of the samples. The mean free path of the electron in solids is inadequate due to a number of interactions, primarily plasmons ones. Then we come to the second part of this, which is dealing with the samples and the thickness. So samples with thickness of only about 100 nanometers are necessary, and they will form the main criteria for proceeding with the analysis work. Now, whether a system can really be investigated by this spectroscopy or not can be seen through this. Henceforth, the electron beam in the spectrometer here has a focal size of the order of 0.5 nanometers, rather millimeters, to that's about this sample size, and it must have a lateral extension also. The evaporated organic film is floated off in a distilled water until it is separated from the substrate. Afterwards, small pieces of the film can be mounted onto standard TEM grids and transformed into the spectrometer. Right panel, which is a typical snapshot of a thin film placed on a standard TEM grid, the diameter of which is 5 millimeters. This is intended for the usage in electron energy loss spectrometer measurements. Subsequent to the evaporation, the films have to be separated from the KBr substrate. For that purpose, the films are floated off in distilled water until the thin film is detached from the substrate and floats at the water surface due to the surface tension. Afterwards, a small piece of the film is mounted onto the standard electron microscopic grids, incorporated into the electron energy loss spectrometer. The sample holder of this is used for this purpose and is transferred into the spectrometer. Continuing with the analysis that is carried out with the help of high resolution electron energy loss spectrometry, the preparation of the thin films starting with single crystals obviously requires a different approach. With the help of an ultramicrotome, a special device allowing precise cuts with the help of a diamond knife. Here in this slide, the simplified view of the preparation process of the thin film has been given. This thin film is used for the investigation using the EELS spectrometer. This has been very beautifully illustrated here in the diagram. It shows a KBr crystals, then it shows a film on the surface which is organic in nature, and then the distilled water which is there has also been shown, and it is this organic film that is going to be analyzed with the help of this spectrometer. It is possible to cut thin slices from a microscopic single crystal. Subsequently, the resulting films have again to be transferred onto a standard electron microscopy grid. This method, however, can suffer from sample hardness or brittleness, which limits its applicability. This spectrometer is an extremely highly sensitive instrument, and any change in the thickness will cause change in the results. Alternatively, one can also try to repeatedly cleave the respective material using an adhesive tape until the film of about 100 nanometer thickness have been achieved. Later, the adhesive tape must be dissolved in an appropriate organic solvent so that the proper analysis can be carried out. A well-known example would be the preparation of thin graphite samples. We have been talking about sample preparation, and under the same heading, graphite samples are the ones which can be prepared where it is even possible to thin the crystal down to a monolayer of graphene. This is also called oxofoliation of graphene. That is, cutting the graphite to a very thin film of the one which can be measured in this kind of spectrometer is called oxyfoliation of graphene.
HREEL spectrometer. In this model, the energy of incident electrons can be varied from 1 to 10 electron volt. To afford high resolution energy, monochromation and analysis are done either with a cylindrical mirror analyzer, cylindrical deflector, or spherical deflector analyzer in combination with retarding field optics of specular. Collection of the backscattered electrons is afforded by rotation of either the sample or the analyzer. Owing the extremely low signals, 10 to 10 angstrom, continuous dynode electron multiplier detector are employed. This model consists of an electron gun, a two-stage monochromator, a single-stage energy analyzer, and a channel electron multiplier detector. Both energy monochromation and energy analysis are carried out with 127 degrees cylindrical deflection analyzer. The incident electrons have an initial energy spread of 0.3 electron volt.
Now we come to data interpretation. This is one of the very important aspects of this study. The technique limits signal to noise ratio of images extracted from spectroscopic mapping, and it depends mainly on the signal processing methods. This is certainly true for energy electron loss spectroscopy, in which pre-edge power, this law in the background modeling can significantly affect the acuteness and the range of the extrapolated determinations. As we have done it earlier, we have determined to enhance the EELS background characterization by two possibilities, or we can say by two methods. Both shall utilize a prerequisite knowledge, that is, the linear combination of power loss and local background of averaging. This LCPL works very good over a range of specimens, but is highly useful when the low background counts would lead to widely fluctuating backgrounds. Now, this works good when the background has been specially oversampled. The two are not mutually exclusive, and this is a very important point and can be combined to give optimal results. They also ignore the distortions to the HREELS fine structures observed with PCA. These algorithms and others have been used through open source software based on the image platform. The Cornell Spectrum Imager provider, it provides a modifiable and extendable high-resolution electron energy loss spectrometer analysis toolset that's available free to the microscopic community. Now, how do we go about spectrum analysis comes in the next part. Proper analysis of the spectral data requires software for extracting the chemical signatures present in a spectrum. For example, software packages like the Cornell Spectrum Images, or as we call it CSI, provides an open source platform for intuitive, advanced approaches to the data analysis and processing of spectral images. It also includes the background estimation and PCA algorithms discussed in this particular module, as well as a graphical interface for the principal component analysis. High resolution electron energy loss spectroscopy has been shown. The kind of spectra that one ultimately gets has been shown here in this slide in the given figure. This talks about a variety of films, of course, variety of thin film. Silver crystal of 110 plane has been taken. Then the thin film on this silver surface, which has been formed with the help of oxygen, has been shown on 110 plane. And then the way it is adsorbed on the surface of silver has been shown, and what way the bonding is there, that also has been indicated in the diagram. Most frequently, HREELS is used to measure adsorbate vibrations, identification of the adsorbate species, the adsorption site, and the spatial orientation of the adsorbate is possible when we analyze the thin film on the surface of any metal in question. Here we have shown the one on silver with 110 plane. HREELS for the study of adsorbate and surface chemistry. What way various adsorbates are adsorbed on the surface is the subject matter of this slide. The various adsorbates would cover the surface and analysis can be carried out with the help of this spectroscopy. Comparison of in specular HREELS spectra recorded after dosing CO2 on a clean left and H covered given on the right side of nickel 110 plane. In this slide, there are two patterns which have been shown. One indicates carbon dioxide dosing on a clean surface which has been given on the left side of the figure, and on the right side we have carbon dioxide covering the nickel surface. The spectra shows that CO2 reacts with H, leading to the formation of formate, as demonstrated by the presence of losses of material at 50, 98, 167 and 365 million electron volts. This has been indicated for two surfaces in this particular slide. This also gives various kinds of adsorbates on these surfaces, or as we say, on targets. It is given in figure A. It is a crystal temperature dependence of the HREEL spectra. The species vibrating at 31 million electron volts converts into the highest frequency one. In B, in specular and ospecular spectra of oxygen adsorbed on silver 210 surface has been given. The decrease of the absolute intensity when moving the O specular is much faster for the 40 million electron volts mode, so that the 56 million electron volts peak dominates the spectrum under these conditions. And in figure C, the dependence of the loss intensifies versus the angle of incidence of the O2 molecules. Depending on what way the angle changes, the intensity's loss can be correlated to that. HREELS, that is this spectra of benzoquinone sulfonic acid chemisorbed on palladium 111 surface, has been indicated. Now this spectra which has been given here indicates the peaks then what gets, and it will give the information regarding the way this compound benzoquinone sulfonic acid will be chemisorbed on palladium 111 surface. This figure given below shows the HREEL spectrum of potassium and cesium plus free palladium 111 3x3 BQSA at layer is giving. The sulfonate group remain intact upon adsorption, as is evidenced by the C bond S and S double bond O stretch mode at 604 electron volt and 1230 electron volts respectively. The presence of the quinoid ring on the surface can be inferred from the CH outer plane bending mode and the in-plane C double bond C and CH slanted flat orientation, or various planes in plane and CH stretches respectively are given at 810, 1466 and 3007 electron volt. Since BQSA is chemisorbed in a slightly slanted flat orientation, the surface dipole selection rule is not strictly enforceable here. Hence, the in-plane stretch mode are observed, albeit at rather low intensities. This is the pattern that one gets on adsorbing this compound on platinum 111 surface. The HREELS experiments on magnesium boron alloy. This is magnesium 10B2 alloy. Again, the peak indicating the adsorption of a compound is there, and what kind of HREELS on MgB2 one can get has been shown in the lower diagram on this slide. A picture of the high resolution electron energy loss spectrometer installed in the SRPES spectrometer is shown here. This will be used to study the electron phonon, electron magnon, electron plasmon coupling. Those might be important in determining material properties. Energy resolution achieved so far is about 2 milli-electron volts as shown in the left figure. The way energy resolution has been shown, it shows that the resolution can be as far as 2 million electron volts. It is given in the figure here. Preliminary experimental results on Mg10B2 alloy at room temperature is shown here. Distinct signature of phonon excitation can be seen in the spectrum. This has been very clearly shown in the figure on the right side. This slide talks about the techniques to detect surface phonons and plasmons. This spectrum which has been shown, where on one side it is loss intensity, on the other side it is loss energy in electron volt, have been given. So one sees the surface phonons, then coordinate bond plasmons, and core level transitions, etc. have been given. High resolution energy loss spectrometer is shown in the figure here in this slide.
Selected application: inorganic molecules. Here we are taking example of carbon monoxide. Carbon monoxide is the most widely used molecular probe in the study of the coordination chemistry and catalytic reactivity of metal surface. The chemioabsorption of CO at transition metal surface is similar to coordinate covalent bond formation in homogeneous metal carbonyl complex. The interaction initially involved a sigma bond formed by the electron pair donation from a filled sp sigma ligand special orbital to an unoccupied d sigma metal orbital. This is followed by a pi bond created by the electron pair back donation from a filled d pi or dp pi metal orbital to an empty 2 pi star ligand orbital. As a result of the surface coordination, the CO bond is weakened and nu CO, the vibrational frequency of the CO stretch mode 1242 centimeter inverse 266 microelectron volt in the gas phase, undergoes an appreciable redshift. The larger the extent of the back donation, the stronger the metal carbon interaction and the weaker the CO bond. The degree of pi back donation is also heightened by the increase in a number of surface atoms breached by the CO ligand. Organic molecules: ethylene. The structure and reactivity of ethylene chemioabsorbed on the transition metal surface are of fundamental importance in the surface science and heterogeneous catalysis. HREELS has been foremost among the surface characterization technique employed. In fact, the first vibrational spectroscopic study of ethylene chemioabsorbed on platinum was carried out with electron energy loss spectroscopy (EELS) almost a decade before IRAS was employed. At temperatures below 200 Kelvin, two types of ethylene-derived surface species have been identified. One is a di-sigma bonded species that result when the CC double bond. Methanol: research activity on methanol has been vigorous because of its commercial importance as an alternative feedstock in fuel cell. When methanol is chemioabsorbed on a catalytic surface at ambient temperatures, it is usually present as a methoxy intermediate. The latter, when undergoes extensive decomposition to yield a product distribution that depends upon the temperature, a tabulation of products generation under various experimental conditions such as metal catalyst and decomposition temperature. Aromatic compounds: an immediate issue in the chemioabsorption of aromatic compounds is whether the phenyl ring is oriented parallel or perpendicular to the plane of the metal surface. In this regard, the intensity of the out-of-plane CH band μCH relative to in-plane CH stretch μCH provides a direct diagnostic indicator of adsorbed aromatic orientation. At specular angle, the dipole selection rule states that μCH for a ring chemioabsorbed completely flat would be EELS inactive. Only the μCH mode would exhibit EELS activity. At off specular angles, the impact scattering selection rule are less restrictive and all modes would conceivably be EELS active, although peak obtained at specular angle would tend to vanish as the off specular angle phi is increased. Organometallic compound. Interest in the structure of adsorbed organometallic compound stems from their capabilities as research laboratory and industrial catalysts. In view of its inherent surface sensitivity and dramatically enhanced resolution, UHREELS has recently become a viable technique in the acquisition of fingerprint spectra of adsorbed organometallic compounds such as the metallocenes. Here, application of polymer in case of HREELS. Only feeble attempts were initially made 2 decades ago in the application of HREELS to the study of polymer surface. The efforts did not become more earnest until a decade later. The use of HREELS has primarily been focused on the following aspects related to polymer film deposited on metals as well as to surfaces of the polymer film themselves, surface morphology, interfacial compositions, the scattering mechanism, and the strength of the polymer substrate bond. The utility of HREELS to probe polymer surface morphology rests on the observation that elastic peaks due to electron backscattered from hydrogen atom can be correlated with the hydrogen content at smooth surface. System that employed HREELS for interfacial composition determination included polyethylene oxide or polystyrene diblock copolymer on silicon wafers, formaldehyde polyoxymethylene film on copper, and Langer Balozat film of 4,4-oxydianiline pyromellitic dihydride polyamide on gold and on highly ordered pyrolytic graphite.
So, having given a details of the introduction and then about the instrumentation and finally about the analysis, we now summarize about what you have learned from this module. The dielectric model holds also when the material on which the molecule adsorbs is not a metal. When measuring the intensity of the electron energy loss peaks and comparing to the other experimental results or to theoretical models, it can also be told whether a molecule is adsorbed normal to the surface or tilted by certain angle. At the incident electron in this model, it has to be scattered in the region above the surface. It does not come to a direct impact at the surface, and as the amount of momentum transferred is whatever value, therefore smaller the scattering of this is very much into the that will result very much into the specular direction. High resolution energy loss spectroscopy is one of the most advanced instruments which is mainly used to obtain the vibrational signatures of surface and the adsorbates on these surface or the adsorbate species under ultra high vacuum conditions. By assigning the vibrational modes of the collected spectrum, the chemical bonding between surface and adsorbate, binding geometry and molecular orientation and ordering can all be identified very properly with the help of this spectroscopy. There are two inelastic excitation mechanisms of the surface vibrational modes: the dipole scattering mechanism and the impact scattering mechanism. The dipole scattering mechanism occurs through an interaction mediated via long range electrical fields set up in both the vacuum and the sample by the probing electron and by the surface excitation. Because the dipole interaction is valid in a range of much greater than atomic dimensions, it can be described uh, densically or in a classical manner also. The dipole scattering mode of this spectrometer is carried out in a specular geometry where the electron incidence angle that can be 60 degrees to the normal of sample surface that is equal to the electron scattering angle. I hope one would be able to appreciate the potential of this spectrometer in terms of surface analysis. Thank you very much, please.